Chapter 1 Aircraft Engines. General Requirements. Aircraft require thrust to produce enough speed for the wings to provide lift or enough thrust to overcome the weight of the aircraft for vertical takeoff. For an aircraft to remain in level flight, thrust must be provided that is equal to and in the opposite direction of the aircraft drag. This thrust, or propulsive force, is provided by a suitable type of aircraft heat engine. All heat engines have in common the ability to convert heat energy into mechanical energy by the flow of some fluid mass, generally air, through the engine. In all cases, the heat energy is released at a point in the cycle where the working pressure is high relative to atmospheric pressure. The propulsive force is obtained by the displacement of a working fluid, again, atmospheric air. This air is not necessarily the same air used within the engine. By displacing air in a direction opposite to that in which the aircraft is propelled, thrust can be developed. This is an application of Newton's third law of motion. It states that for every action there is an equal and opposite reaction. So, as air is being displaced to the rear of the aircraft is moved forward by this principle. One misinterpretation of this principle is air is pushing against the air behind the aircraft, making it move forward. This is not true. Rockets in space have no air to push against, yet they can produce thrust by using Newton's third law. Atmospheric air is the principal fluid used for propulsion in every type of aircraft power plant except the rocket, in which the total combustion gases are accelerated and displaced. The rocket must provide all the fuel and oxygen for combustion and does not depend on atmospheric air. A rocket carries its own oxidizer rather than using ambient air for combustion. It discharges the gaseous byproducts of combustion through the exhaust nozzle at an extremely high velocity, action, and it is propelled in the other direction, reaction. The propellers of aircraft powered by reciprocating or turboprop engines accelerate a large mass of air at a relatively lower velocity by turning a propeller. The same amount of thrust can be generated by accelerating a small mass of air to a very high velocity. The working fluid, air, used for the propulsive force is a different quantity of air than that used within the engine to produce the mechanical energy to turn the propeller. Turbojets, ramjets, and pulse jets are examples of engines that accelerate a smaller quantity of air through a large velocity change. They use the same working fluid for propulsive force that is used within the engine. One problem with these types of engines is the noise made by the high-velocity air exiting the engine. The term turbojet was used to describe any gas turbine engine, but with the differences in gas turbines used in aircraft, this term is used to describe a type of gas turbine that passes all the gases through the core of the engine directly. Turbojets, ramjets, and pulse jets have very little to no use in modern aircraft due to noise and fuel consumption. Small general aviation aircraft use mostly horizontally opposed reciprocating piston engines. While some aircraft still use radial reciprocating piston engines, their use is very limited. Many aircraft use a form of the gas turbine engine to produce power for thrust. These engines are normally the turboprop, turboshaft, turbofan, and a few turbojet engines. Turbojet is the former term for any turbine engine. Now that there are so many different types of turbine engines, the term used to describe most turbine engines is gas turbine engine. All four of the previously mentioned engines belong to the gas turbine family. All aircraft engines must meet certain general requirements of efficiency, economy, and reliability. Besides being economical in fuel consumption, an aircraft engine must be economical in the cost of original procurement and the cost of maintenance, and it must meet exacting requirements of efficiency and low weight to horsepower ratio. It must be capable of sustained high power output with no sacrifice in reliability. It must also have the durability to operate for long periods of time between overhauls. It needs to be as compact as possible yet have easy accessibility for maintenance. It is required to be as vibration-free as possible and be able to cover a wide range of power output at various speeds and altitudes. These requirements dictate the use of ignition systems that deliver the firing impulse to the spark plugs at the proper time in all kinds of weather and under other adverse conditions. Engine fuel delivery systems provide metered fuel at the correct proportion of air fuel ingested by the engine regardless of the attitude, altitude, or type of weather in which the engine is operated. The engine needs a type of oil system that delivers oil under the proper pressure to lubricate and cool all of the operating parts of the engine when it is running. Also, it must have a system of damping units to damp out the vibrations of the engine when it is operating. Power and weight. The useful output of all aircraft power plants is thrust, the force which propels the aircraft. Since the reciprocating engine is rated in brake horsepower, bhp, the gas turbine engine is rated in thrust horsepower, THP. The value of 375 mile-pounds per hour is derived from the basic horsepower formula as follows. 1 horsepower equals 33,000 feet to pound per minute or 375 mile-pounds per hour. Under static conditions, thrust is figured as equivalent to approximately 2.6 pounds per hour. If a gas turbine is producing 4,000 pounds of thrust and the aircraft in which the engine is installed is traveling at 500 miles per hour, the THP is. It is necessary to calculate the horsepower for each speed of an aircraft, since the horsepower varies with speed. Therefore, it is not practical to try to rate or compare the output of a turbine engine on a horsepower basis. The aircraft engine operates at a relatively high percentage of its maximum power output throughout its service life. The aircraft engine is at full power output whenever a takeoff is made. It may hold this power for a period of time up to the limits set by the manufacturer. The engine is seldom held at a maximum power for more than 2 minutes, and usually not that long. Within a few seconds after liftoff, the power is reduced to a power that is used for climbing and that can be maintained for longer periods of time. After the aircraft has climbed to cruising altitude, the power of the engines is further reduced to a cruise power, which can be maintained for the duration of the flight. If the weight of an engine per brake horsepower, called the specific weight of the engine, is decreased, the useful load that an aircraft can carry and the performance of the aircraft obviously are increased. Every excess pound of weight carried by an aircraft engine reduces its performance. Tremendous improvement in reducing the weight of the aircraft engine through improved design and metallurgy has resulted in reciprocating engines with a much improved power-to-weight ratio, specific weight. Fuel economy. The basic parameter for describing the fuel economy of aircraft engines is usually specific fuel consumption. Specific fuel consumption for gas turbines is the fuel flow measured in pound per hour, divided by thrust, lb, and for reciprocating engines the fuel flow, pound per hour, divided by brake horsepower. These are called thrust-specific fuel consumption and brake-specific fuel consumption, respectively. Equivalent specific fuel consumption is used for the turboprop engine and is the fuel flow in pounds per hour divided by a turboprop's equivalent shaft horsepower. Comparisons can be made between the various engines on a specific fuel consumption basis. At low speed, the reciprocating and turboprop engines have better economy than the pure turbojet or turbofan engines. However, at high speed, because of losses in propeller efficiency, the reciprocating or turboprop engine's efficiency becomes limited above 400 miles per hour, less than that of the turbofan. Durability and reliability. Durability and reliability are usually considered identical factors since it is difficult to mention one without including the other. Simply put, reliability is measured as the mean time between failures, while durability is measured as the mean time between overhauls. More specifically, an aircraft engine is reliable when it can perform at the specified ratings in widely varying flight attitudes and in extreme weather conditions. Standards of powerplant reliability are agreed upon by the Federal Aviation Administration, FAA, the engine manufacturer, and the airframe manufacturer. The engine manufacturer ensures the reliability of the product by design, research, and testing. Close control of manufacturing and assembly procedures is maintained, and each engine is tested before it leaves the factory. Durability is the amount of engine life obtained while maintaining the desired reliability. The fact that an engine has successfully completed its type or proof test indicates that it can be operated in a normal manner over a long period before requiring overhaul. However, no definite time interval between overhauls is specified or implied in the engine. Rating. The time between overhauls, TBO, varies with the operating conditions, such as engine temperatures, amount of time the engine is operated at high power settings, and the maintenance received. Recommended TBOs are specified by the engine manufacturer. Reliability and durability are built into the engine by the manufacturer, but the continued reliability of the engine is determined by the maintenance, overhaul, and operating personnel. Careful maintenance and overhaul methods, thorough periodical and pre-flight inspections, and strict observance of the operating limits established by the engine manufacturer make engine failure a rare occurrence. Operating flexibility. Operating flexibility is the ability of an engine to run smoothly and give desired performance at all speeds from idling to full power output. The aircraft engine must also function efficiently through all the variations in atmospheric conditions encountered in widespread operations. Compactness. To effect proper streamlining and balancing of an aircraft, the shape and size of the engine must be as compact as possible. In single-engine aircraft, the shape and size of the engine also affect the view of the pilot, making a smaller engine better from this standpoint, in addition to reducing the drag created by a large frontal area.